Isn't it amazing that all this mathematical things and knowledge about all the quantum stuff just started off with some ancient civilization wanting a better way to know how many sheep they had than a lot or not many?
Well, yeah, it is. It is. And in fact, it's not just amazing, it's really strange. It's really hard to understand. And it's what a physicist called Eugene Wigner referred to as the unreasonable, no, it's Hermann Weyl, the unreasonable effectiveness. Now I'm confused. Which was it? Weyl or Wigner? It was Wigner. It was Wigner. Who talked about the unreasonable effectiveness of mathematics. Why should it be that maths seems such a good way for us to understand the universe? And to understand, it's fine that it would be useful for counting your sheep. It's fine that it might, help you to build pyramids, but why should it continue to be useful for doing stuff like, quantum mechanics, for understanding this very fundamental sort of aspect of nature? And no one really knows why maths should be so useful for doing that. I don't think anyone has ever really satisfactorily answered that problem. And it touches on this same question. How far can we trust maths? Can we be sure that it's kind of maths all the way down? One possibility that, some of these ideas about how we perhaps ought to be thinking about what's underneath quantum mechanics, one possibility is that actually it's random. But it's a kind of randomness that once we start looking at it as humans, quantum mechanics is the mathematical machinery that we need to make sense of it, but that fundamentally there are no rules, there are no laws. In fact, this is what I mentioned John Wheeler, who was a very profound thinker about quantum mechanics, and he started to suspect that there was fundamentally something he called law without law. He loved saying things like this, that what it meant was that there were no laws at the very fundamental scale of nature, but somehow mathematical laws emerge out of them. And that's possible, but we don't know.
What'll really mess with your head is, did the mathematicians discover things or invent them?
Yeah, it's like, is math something that humans have invented to make sense of the universe, the vastness of it? Or is it something that some big part of the universe that humans have happened to have stumbled upon, like?
Nobody knows, and I certainly don't. That question is still argued about. It's a great question, though.
I have a question on the back row there. Can we get a mic? Sorry, I should have said earlier so we could get the microphone up, but thanks.
I'm lost. Who had that?
Can you put your hand, wave your hand back so they can see you? Sorry.
Thanks. Would it be easier to digest the ideas that you put forward about quantum mechanics if we were to forget entirely Newtonian physics and start again from scratch?
I don't know. I don't think we can. And in fact, I don't think we should, because Newtonian physics works fantastically. It got us to the moon. It's exactly what we need to predict how everyday objects are going to move about. I think what I found it very interesting is that we now have a not complete understanding, but a much better understanding, certainly than Bohr or Einstein did, of why we have classical Newtonian mechanics as a result of quantum mechanics. We can understand, using ideas about entanglement and decoherence that I mentioned, why it is that these particular rules, these particular classical rules of physics, seem to emerge from the quantum sort of substratum. We don't have a complete understanding of that, but we know quite a lot about how it does. So, in a way, I think you could see that as a validation of Newtonian physics as the right approximation for us to use at these everyday scales. But I think that perhaps the problem that we encounter when we try to talk about quantum mechanics, and the kind of problem that leads to those things that I quoted at the start and then drew a big cross through, is that because this is our only experience, classical physics, all the stories that we tell are kind of classical stories about particles taking paths and taking all paths at once, but we're still fixed on this idea that they have trajectories. It's just that we have to somehow, multiply them and say that something weird is happening. So the stories that we try to tell about quantum mechanics seem always to be classical ones, and that's the problem, because they won't work. They'll always, at best, be a crude approximation, and sometimes they'll just be the wrong stories. So I think classical physics is fine, but we do need to get out of that mindset as much as we can when we're trying to talk about quantum mechanics.
Okay, we have a question up on the balcony there.
I have two questions. The first one is, if you sent two entangled particles to each side of the universe and you could affect the spin of the particles, could you use that as an instant form of communication as a binary code?
Yeah, good. That is a great question. And the answer is simply no, you couldn't. Sadly, and that's kind of what I was talking about, that actually you can discover that there seems to be this correlation between those two particles, but you can only discover that by finding out, what the other particle was measured as. And what that means is that you can't actually use it to send any signal, because Alice over on this side of the universe seems to, when she makes a measurement, it looks to her as though that measurement is random. There's no reason for her not to think that, until she knows that Bob's particle was correlated, was opposite. And so the measurements just look random until we have that information about what Bob's measurements were. And that's what stops you sending any kind of meaningful information. So sadly, you can't.
And my second question is, if you can measure the energy in the light you send to a particle, could you find both the velocity and the position?
If you could measure the energy
in the light that you send, because you have the process.
Could you find both the velocity and the position?
Yes.
This is touching on Heisenberg's uncertainty principle, which I stated in its kind of wrong or misleading form at the beginning, because although that's often the way it's stated, that you can never measure the position and the velocity of a particle at the same time. Actually, you can. Heisenberg never said you couldn't measure the position and the velocity. All he said was you can't measure them both to an arbitrarily precise accuracy. There's a limit to how accurate you can be. So if you know the position more precisely, then you're going to have more uncertainty in the velocity. And there's a very precise mathematical relationship that Heisenberg stated that relates those two things. And I think it's also important to say that applies to position and velocity. It also applies to some other pairs of measurements of properties of quantum particles that you could measure. But it doesn't apply to them all. It's not some general property that if you measure one thing precisely, you can't know another thing with arbitrary precision. It only applies to certain pairs of properties. And you can see what these are from quantum mechanics. So it's important to recognize that Heisenberg's uncertainty principle is actually a very precise principle. It's not just some generalized thing that says you can't know everything. Because you can know an awful lot. You can't know everything, but you can know an awful lot without being troubled by Heisenberg's uncertainty principle.
So I have a question, if I may. Which is that, sorry, I'll get back to the audience in a minute, but that as a working physicist, right, and doing weird stuff at CERN, I still have in my head no problem with the idea. In fact, I've resolved this in my head, that the interaction with the environment, this spreading out of the quantumness, the decoherence that you talked about, is what makes the measurement. So there's no need for a human being to open the box. The cat itself is big enough to decohere the wave function, and that's fine. And then on top of that, it's actually completely random. So the choice that's actually made is made at some point in that decoherence, and it is utterly random. And that's that. And that's how I sleep at night. Is that consistent? Is that consistent with what you're saying, or does that still leave a problem open? What's the problem with that, I guess?
Yeah, it is consistent with what I'm saying, and it's why, I think Schrodinger's cat, it's time to kill it, really. It's not a great thought experiment because, for all sorts of reasons. For one thing, because to really do an experiment like that, you need a quantum property that you can measure. Well, being alive or dead isn't a quantum property. We don't know how to express that in quantum terms. But also, you're quite right that if you just stuck a cat in a box with this with this sort of let's say a spin that's going to be either up or down that will kill it or not kill it, you will get this decoherence without having to look, because the cat is interacting with its environment, and that alone is enough. You could say the universe is always watching. There's always this decoherence going on. But you could say, well, what if we could isolate the cat sufficiently that you don't get decoherence? What if somehow, God knows how, because you might need a high vacuum, you might need very cold temperatures, but if somehow we could stop that decoherence from happening by isolating the cat sufficiently from its environment, what then? And actually, it's not really clear what quantum mechanics does say then. In fact, quantum mechanics really does say if you could get that situation, and it's really pretty much impossible to see how you could, but if you could, you would have to say the cat is in a quantum superposition.
So where between the cat and the rest of the universe is big enough system to decohere? I thought the cat was big enough on its own to decohere.
It has to. Well, if you can isolate the cat from everything else and just couple it to this quantum object, then the decoherence can't go any further. The cat has to be then entangled with the quantum object. Now, I still think that's a rubbish scenario because you can't.
I might not sleep well.
Because you can't express that in quantum terms. You can't write an equation for an entangled cat, but you can write an equation for a load of particles. Let's say ultra cold particles, billions of them, of atoms that are entangled in some sense. And this is what people are now doing. They're doing experiments kind of in the middle between the size of a cat and the size of atoms, seeing how big you can make a system that you can still control well enough that you can prevent decoherence, and can you then see things like superpositions? Mm-hmm. And so far, it seems clear that you can. The latest is that some researchers made the tiny little microscopic beams out of silicon that can vibrate. And if you're very careful when you cool it down enough, those vibrations are quantum vibrations. They're described by quantum mechanics. And you can place that beam in, you can entangle two beams so that they're vibrating in an entangled way, and you can show that they are entangled. So these are things that you can certainly see in an electron microscope. They're not atoms, they're kind of big stuff, still microscopic. And sometimes these things are called Schrodinger kittens. And the question is, how big can your kitten get?
Okay, thanks. Question there? Two questions, so if you can get the mic, so there's one in front and then one behind. So. You have to put your hands up so people can see where to send the mic.
I'm not sure where it's going.
Okay, the one at the back is where
I have two questions. So when the universe started during the Big Bang, weren't equal quantities of matter and antimatter be formed? And if so, how did our pockets of normal matter come to be? Why, if equal amounts were created, then why didn't they just destroy each other and we still have nothing?
You see, this is why I need John, because quantum mechanics, as it stands, isn't going to answer that. That's a deep question for fundamental physics that we're going to need another theory to explain why it is that it seems that actually there is an asymmetry between the amount of matter and antimatter in the universe. We don't really have an explanation.
We don't know. If
why
I could give
is.
you an evidence-based correct answer to that right now, I'd go off and get a Nobel Prize.
You would.
We actually don't know. It's one of the things we're studying at CERN actually at the moment.
Yeah.
And also, from my understanding, the Manyworlds theorem means that, say you flip a coin, pretty much the universe kind of splits in half. One side of the coin is heads, and the other universe of the coin is tails. Is that true?
Is that true? Okay, it's true that that's what the Manyworlds interpretation would have you believe. and there it stops. I mean, but actually, I think one of the things that disturbs me, there are many things that disturb me about Manyworlds interpretation. The fact that it predicts countless universes isn't one of them. Who are we to say? That doesn't bother me. But what does bother me is that that's often the way it's talked about. You flip a coin or you do a quantum experiment, you measure a spin, and the universe splits. But if you really take it seriously, the universe has to be splitting every time a quantum interaction, two quantum particles, leads to decoherence, leads to a particular outcome. While they stay in a superposition or entangled state, that's fine. But every time they decohere, then you have to have a splitting of worlds. And that would have to be happening more times than you can possibly imagine, all the time in all of our bodies. Every sort of interaction of a protein or anything else, or any, pretty much any molecular process leads to a particular outcome. Okay, it doesn't stay entangled, decoherence happens. So it means, this idea that you casually sort of split the universe every so often when you make a measurement isn't really what the Manyworlds interpretation is about. It's about a proliferation of universes all the time beyond, measure, beyond imagining. And in particular, what it means is that it's happening far more often and far quicker than the speed of thought, which means I don't really understand what an individual means, what a person means, let alone this notion that each of us is sort of splitting. We're splitting faster than our thoughts can occur. What does that mean? Where do we get a coherent sense of our individuality and our coherent experience out of that? I'm really not sure. There are all sorts of other problems with the Manyworlds interpretation, but I think, then I'm not being flippant when I say this, that perhaps the simplest answer I could give is that if it's true, it really doesn't matter how I answer your question, because I have answered it in other ways in every other universe. There was a question. Yes.
This question is related to the very big and the very small, where there is this kind of a division, sort of an event horizon between quantum mechanics and classic Newtonian sort of physics. Do the properties of matter flip at that point, or is there a continuum?
Well, there is a continuum. I mean, I think this is what we're talking about in terms of this notion we now have that Bohr didn't have, for example, of decoherence. That this is, how that transition from quantum to classical is now talked about. That it's a gradual thing. That the kind of notion now is that classical physics gradually emerges. I mean, I say gradually, it emerges very quickly because decoherence happens almost instantly for large objects. But it happens through that process. As decoherence happens, so we get classical-like behavior. And we can actually see that happening. There have been experiments that show that can control the rate of decoherence. Basically, one of them involves firing molecules through this. It's a classic double slit experiment where you see a particle, again, it seemed to go through both slits at the same time and cause an interference pattern, as if it's sort of a wavy particle. But you can control the rate at which decoherence happens in that system by just letting more gas in to sort of interact with the particles, the molecules that are going through the slits, and spreading the quantumness. And as you control the amount of gas that's in there, so you make decoherence happen at a greater and greater rate, you see a disappearance of the interference pattern. So you can watch decoherence happen. So we know it's a real physical process. So this is the way that quantum to classical transition is now talked about. And that's a big advance over the way what Bohr had to say, and what lots of people don't like, and rightly don't like, about the Copenhagen interpretation, is that he seemed to be just making a sort of hard and fast division between quantum and classical. And I don't think he was ever saying there's suddenly a weird sort of flip one to the other. He didn't imagine, because it simply wasn't imaginable at his time, that you'd ever be able to get to look at that nebulous, that grey territory in between to see what goes on there. but now we can. And so now we have a better picture of how quantum becomes classical. But I don't want to imply from that it's all explained and that we know how we get to this state from quantumness, because decoherence, the theories about decoherence get you a long way towards that understanding, but there's still some things that it can't really tell us. And in particular, what it can't really tell us is why you only get one outcome, why you get a unique outcome from that process. Because as far as you can see, if you follow it through, decoherence through, all of them still remain possible in principle. Where does this, it still feels like somehow there's a collapse to a single outcome, and we can't really explain that. And of course, the Manyworlds interpretation says, well, that's because there isn't one. Relax. If you just assume there isn't one, it's all fine. I can understand that motivation, but I think if you assume that, there are other problems that arise. And that's where I say, we don't have a full understanding of what quantum mechanics is really about and how it leads to the world as we know it. But we do know a lot more.
Okay, we had a question up on the balcony again now.
So, to my understanding, quantum physics and relativistic physics have a bit of an incompatibility, which means we're having a bit of a problem making some kind of theory of everything. Why is there an incompatibility between the two?
Well, and this is why people are pursuing ideas in particular like string theory, because there is a hope that string theory will provide that merging of quantum physics, of quantum mechanics, and general relativity, because these little strings that it posits are basically quantum entities that are vibrating in some quantum way. But it seems that out of this, you might be able to get some description of gravity. So this is the quest that people are after, a quantum description of gravity. And one way, there's various ways of thinking about this, but I suppose one simple way is that if you follow general relativity to understand what happens inside a black hole, then it predicts that the collapse just continues. Though stars, black holes are made by stars collapsing under their own gravity, and in general relativity, there's no end to that process, and they collapse down to an infinitesimally small point. But quantum mechanics says that's impossible. There are no infinitesimally small points, because once you get below a certain size scale, it's very, very small, much smaller than atoms, much smaller than the bits of atoms that we know about. But once you get down there, there's a sort of granularity. You can't get beyond that. The laws of physics can't, as we know them, can't operate in that very small vicinity. So that's really the basic incompatibility, that general relativity assumes that there's a continuous, that everything is kind of continuous and smooth, whereas quantum mechanics says, no, it's not. It has this granularity. Do you want to add anything?
No, I think that's the nub of it. The general relativity assumes a continuous space-time, and when you get to very high energies or very short distances, that's incompatible with quantum mechanics. It has to be quantized, and no one's worked out how to quantize space-time properly. Yeah. So down here, maybe just two more questions, I think. So here's one down at the front, and then one last one, and then you can go and sign your books.
When you were saying that particles are entangled on both sides of the universe, i.e. spin up and spin down, you were saying there's a correlation there. So one particle is sort of in the know to what the other particle is doing. So if that correlation is not information, what exactly is it?
Yeah, that's the question. That is exactly the right question. And the answer is, we cannot say, and that's not my, happily, I'm confident that's not just my ignorance. For example, one of the most respected physicists in the world, David Mermin, has said, entanglement means there are correlations for which we have no physical explanation. Okay, but one thing we can say is that you said, so there's this particle here and there's this particle here, and somehow they seem to know what each other is doing, but how can that be possible without information? Well, I think the real issue there is that entanglement says we can no longer talk about the particle here and the particle there. In quantum mechanics, the description that quantum mechanics gives says that those are parts of a single entity. doesn't seem to make sense how that can be when they're separated by the size of the universe in principle. How can an entity be that big? And how can it pay no attention, seemingly, to the amount of space, distance that has come between them? But quantum mechanics says it can. This is what quantum non-locality means. It seems to create a nonsense out of our everyday notions of space and time, actually. And this is a real problem to figure out how to talk about this. But I think that the key might be to, at least to begin with, to recognize that when things are entangled, they're part, as far as quantum mechanics is concerned, they're part of the same entity. They're no longer this particle and that particle. It does sound strange, but that's quantum non-locality.
Okay, thank you. Do we have one last question? There, the guy with the yellow tie was slightly ahead, I think.
Thank you. In the game where you describe sending someone out of the room and then they come back and ask these questions, the questions get progressively more and more difficult, but eventually they reach a solution. Is there any guarantee that a solution exists?
Well, if you're playing the game properly, then there is, because you have to have, in order to answer, you have to have someone in mind. So there has to be a solution in order to give any answer at all. There may be cases, I haven't thought this completely through, but now that you ask, it's a great question, because there may be cases where you can't think of an answer, and where you have to then answer at random, and the answers then kind of lose their coherence. And some people think that this is kind of analogous to what is happening in quantum systems, that there's a certain amount of information that they can hold. And once you've asked enough questions to exhaust that information, anything else you ask must be random. Okay, and that's really what's happening in this case of entangled particles. Because one way of thinking about it is to say they can only hold so much information between them. If we exhaust that information by stipulating the correlation they have to have, one up and one down, then when we ask, okay, but which way will it be? It's random, because there's no information capacity left to hold that information. All the capacity is exhausted by the correlation between them. So that's another way to think of it, and I hope that makes sense. But
Thank you very much.
I find it a useful way to think about it, this notion of a limit to the capacity of information that the universe can hold. And we can ask more questions than that, but we're not going to get more answers. And I think, it may be that is why we get this randomness and this seeming strangeness out of the quantum world.
What a great note to finish on. So thank you very much. And